this video, I'd like to talk about some special examples of series, and these are called telescoping series. I'm going to go through a couple of these examples, but really to point out what makes them a telescoping series, you should notice that the terms of the series consist of a difference. So we're looking at this example here, and the two things in that difference look very similar to one another. So that's all a little vague, but we're going to see why that somewhat vague description is important. So at this point, we've defined what it means for a series to converge, and we've defined it as relating to the limit of the nth partial sum. So with that being what we have as our only tool, let's think about actually trying to find the nth partial sum. So to start with, I can find the first partial sum. Recall the first partial sum is just the sum of the first term, which is just the same thing as the first term. That would be 1 minus 1/2. Now I can write that as 1/2, but when you're doing this process for telescoping sums, it's often the case that simplification is going to make it much harder to see the outcome. So I encourage you to not simplify. Then S2 would be the sum of the first two terms. So I write down the first term from above, and then the second term occurs when k is equal to 2. And S3 would be the sum of the first three terms, which that third term occurs when k is 3. And right away, one of the things that I can notice here, which is a hallmark of telescoping sums, is some cancellation. So notice the 1/2s cancel, and in fact, those should likewise cancel for any later partial sum. Then when I get to the third partial sum, the 1/3 terms cancel, and those should cancel for anything beyond that. And this should continue that each time I take a higher partial sum, one more cancellation occurs. So with that in mind, we can notice a pattern. And I can see that this is 1 minus 1/2. This is 1 minus 1/3, 1 minus 1/4. And by writing out this pattern, my goal is to find the nth partial sum. So notice that I can look at the dependence at this point between the subscript and what's being subtracted. So certainly the 1 is going to be there. That won't be canceled. And what I'm seeing from the pattern above is that when I'm looking at S sub n, what seems to be subtracted is 1 over n plus 1. This is what we call a closed form expression of the nth partial sum. This is much preferable to simply writing out the sum of the first n terms with ellipses. And in particular, writing my nth partial sum like this makes it so that I can find the limit as n approaches infinity of the nth partial sum. So in taking this limit, notice that we just get 1. Recall then from our definition, we see that the sequence of partial sums converges to a finite value, and that means that the series converges, and on top of that, we can actually say that the series converges to 1. And again, another way of saying that is the sum of the series is 1. So telescoping sums end up being a really nice place to be able to directly apply the definition of convergence. Not all telescoping sums converge, so that's not a necessary result for them. Here's another telescoping sum. Again, notice the terms involve a difference, and what you're subtracting looks very similar to the positive part. If I suspect that it's telescoping, my immediate approach is to list out partial sums. So the first partial sum is when k is 1, so that should be log of 2 minus log of 1. And again, I'm not going to simplify. The sum of the first two terms would then tack on a log 3 minus log 2. The sum of the first three terms would be the same as the one above, plus the third term, which is natural log 4 minus natural log 3. And again, I can pause and observe some cancellations. This log 2's cancel from here on out. The log 3's will cancel. And I'm at a point where I can find the nth partial sum. So it seems that the minus natural log of 1 will never cancel. And in fact, natural log of 1 is 0, so that's not terribly important. But at any given point, there will be a positive log term that has not yet canceled. And again, I want to decide how what is in the log matches up to the subscript. So again, we can see that the comparison is that it's 1 greater than the subscript. So if I want to now take the limit as n approaches infinity of the nth partial sum, that means I'm taking the limit as n approaches infinity of natural log of n plus 1, and that goes to infinity. So that limit is not finite. So this means that in answer to the question, does the series converge? The answer would be no, the series diverges. So this will be clearer when I go through some other examples, but one thing to point out is there's some kind of coincidence with my two examples. So it's not always the case that the pattern is that you've got an n plus 1 involved. That's what we had here. It can vary what that is represented as. And the other thing, I seem to somewhat arbitrarily find 3 partial sums and then stop. We're going to see an example or several examples where it might take a little bit longer for the cancellation to occur. And what that really is a factor of is the difference between these. So these only differed by 1. So it only took me to the second partial sum to see cancellation. We're going to see if you had, say, k plus 3 in k, it would take you to the fourth partial sum to see cancellation. So the meaning of that is that if you do encounter an example and you don't right away notice cancellation, it might just take a little bit longer. And then one last example here. What I want to emphasize here is this is not telescoping. It's not even a difference. It's not something that I could express as a difference. So, but suppose that even though it's not telescoping, what would it look like if we tried to approach it the same way? Well, we can find partial sums for any series. The first partial sum is the first term. The second partial sum is the sum of the first 2 terms. Whoops. Third partial sum is the sum of the first 3 terms. Whoops, keep doing that. So notice that there's no cancellation here, and in particular, there's no obvious way to simplify the nth partial sum, which at best I could start to express as 1/2 plus 2/3 plus 3/4 ... through n over n plus 1. So I can write it like that, but being able to write it like that doesn't allow me to find the limit. So we can't find the limit as n approaches infinity of s of n. And the reason is certainly n shows up in here, but the implication is that as I increase n, the number of the terms is increasing as well. So this is a very complicated problem. If I can't get from writing out the terms by listing them to something where I have what I called before a closed form expression, like we had up here, where it's very simple to just take the limit, then using the definition directly is not going to be helpful. And we're going to see that most of the time, this is the situation we're going to fall into. It's not telescoping. There's not something really very simple about writing out the partial sums. In cases like this, that's when we're going to want to resort to something else, which we haven't covered yet. And that something else is going to include what we call tests for convergence and divergence.